In the winter of 1960, while the world watched American astronauts prepare for Mercury launches under brilliant floodlights and press conferences, a different kind of space program gathered in the frozen outskirts of Moscow, where engineers stamped their feet against the cold in unheated assembly buildings and discussed trajectories to Mars in whispers. The Soviet Union had already shocked the world with Sputnik, already sent dogs into orbit, already claimed the high ground of space as socialist territory. But these achievements existed in a strange duality with the failures that accumulated in filing cabinets marked for destruction. The Mars program began not with a grand announcement, but with a series of internal memos circulated among design bureaus that had learned to communicate in coded language, where the word Mars itself became a kind of classified information, spoken only in secure rooms where the air tasted of cigarette smoke and nervous ambition. The logic driving this secrecy operated on multiple frequencies simultaneously. On one level, the Cold War demanded spectacular achievements that could be broadcast to prove Soviet technological supremacy, to demonstrate that dialectical materialism produced better rockets than capitalism, to show colonized nations that the future belonged to the Red Banner. On another level, this same Cold War created a terror of failure so profound that entire missions would be erased from public record, their wreckage scattered across Kazakhstan or lost in the frozen Pacific, their existence denied even as Western intelligence agencies tracked their radio signatures. The tension between these imperatives created a program that operated in shadows even when it succeeded, that claimed credit cautiously and denied failure absolutely, that treated each launch as both a propaganda opportunity and a potential catastrophe that might never have officially occurred. The engineering that emerged from this environment bore the marks of its creation. Soviet rocket technology in the late 1950s represented an accumulation of captured German designs, indigenous innovation driven by brilliant mathematicians working in closed cities, and the brutal efficiency of a system that could marshal unlimited labor and resources towards singular objectives. The R-7 rocket that launched Sputnik became the foundation for an entire family of launch vehicles, each iteration adding stages and capability, each modification classified and tracked through designation systems that confused even the engineers who built them. When the Mars program began, it inherited this infrastructure of secrecy, adding layers of its own as missions were designated with numbers that revealed nothing, as payloads were described in vague terms even within internal documentation, as failures became state secrets and successes became carefully managed revelations. The first attempts to reach Mars emerged from the design bureau led by Sergei Korolev, the chief designer whose identity remained classified even as his rockets reshaped human capability. The 1M program represented the Soviet Union's initial thrust toward Mars, crude spacecraft by later standards but ambitious beyond anything attempted before 1960. These vehicles weighed over a ton, carried instruments designed to measure radiation and magnetic fields during the journey, and relied on trajectories calculated by hand using logarithm tables and mechanical computers that filled entire rooms with clicking relays. The mathematics of interplanetary flight presented challenges that extended beyond simple orbital mechanics. A spacecraft bound for Mars had to leave Earth's gravitational well at precisely the correct velocity and angle, had to account for the gravitational perturbations of the Moon during its escape, had to aim not at where Mars appeared in the sky, but where Mars would be months later when the spacecraft finally arrived, traversing hundreds of millions of kilometers through a void where the slightest error in initial conditions would compound into mission failure. The launch windows for Mars missions opened only once every 26 months, when the orbital geometries of Earth and Mars aligned in configurations that permitted fuel-efficient transfers. This astronomical constraint created a rhythm of desperation in the Soviet program, where teams would work around the clock as launch windows approached, knowing that any failure meant waiting more than 2 years for another opportunity, knowing that American programs were preparing their own attempts, knowing that political leaders expected results that could be announced in time for party congresses or anniversaries of the October Revolution. The pressure manifested in mistakes that engineers recognized too late, in shortcuts that seemed justified under deadline stress, in decisions to launch vehicles that carried known defects because the alternative was missing the window entirely. The first 1M mission launched on October 10, 1960, aboard a Molniya rocket that represented the cutting edge of Soviet capability. The vehicle cleared the launch pad successfully, ascending through the cold morning air above Baikonur, climbing toward the altitude where its upper stage would ignite and push the payload toward escape velocity. Then, 90 seconds into flight, a strap-on booster separated prematurely, throwing the rocket into a catastrophic tumble that ended in a fireball visible from the control bunkers. The spacecraft, designated 1M number 1, never reached orbit, never transmitted a single byte of data, never officially existed in any public record. The failure investigation consumed weeks, revealing subtle flaws in the separation mechanism, but the window was already closing. A second attempt launched 4 days later using 1M number 2, an identical spacecraft mounted on a rocket that had passed the same inspections as its predecessor. This mission survived stage separation, achieved a parking orbit around Earth, then watched its escape stage fail to ignite, leaving the spacecraft trapped in a decaying orbit that would bring it back into the atmosphere within days. The official Soviet news agency TASS announced nothing. Western tracking stations detected the signals and noted the failures, but without imagery or official confirmation, these became ghost missions, suspected but unverified, existing in the ambiguous space between rumor and fact. The erasure of these failures from public record created a historical gap that persists decades later. Soviet engineers who worked on the missions carried their knowledge into retirement, sometimes dying without ever speaking publicly about what they had built, and watched explode or fall silent. Documents that survived the collapse of the Soviet Union often existed in fragments, scattered across archives that resisted organization, written in technical shorthand that assumed readers possessed classified context. The result is a history that must be reconstructed from signals intelligence, from brief mentions in obscure technical journals, from the memories of aging engineers who finally spoke as state secrecy dissolved, and from the physical evidence of hardware that occasionally surfaces in storage facilities or museums, labeled with designations that match no official records. After the 1M failures, the program evolved into the 2MV series, which introduced greater sophistication in spacecraft design and mission architecture. The 2MV program actually encompassed 3 distinct types of missions, each identified by a numerical suffix that indicated its intended purpose. The 2MV. One variant was designed as a Mars flyby spacecraft, intended to pass close to the planet while gathering images and scientific data before continuing into heliocentric orbit. The 2MV-2 variant carried a lander that would separate from the main bus and descend to the Martian surface, making the Soviet Union the first nation to place hardware on another planet. The 2MV-3 variant was configured as a Venus flyby, representing the parallel track of Soviet planetary exploration that often competed for resources and political attention with the Mars program. This proliferation of mission types reflected both the ambition of Soviet planners and the improvisational character of a program that had to adapt quickly to failures, repurposing hardware and adjusting objectives as circumstances demanded. The 2MV spacecraft introduced innovations that would influence Soviet planetary exploration for years. The basic design featured a cylindrical body with solar panels extending like wings, an orientation system that used sensors to lock onto the Sun and Earth for navigation, and instruments mounted on a scanning platform that could point independent of the main spacecraft. The mass budget for these vehicles exceeded 800 kilograms, enormous by the standards of 1960s deep space exploration, requiring powerful upper stages that pushed the limits of existing rocket technology. The spacecraft carried cameras using film that would be developed on board using automated chemical processes, then scanned and transmitted back to Earth as radio signals that required enormous dish antennas to receive. The engineering represented a convergence of optical mechanics, chemistry, radio electronics, and precision manufacturing, all of which had to function reliably across millions of kilometers in an environment of vacuum, radiation, and temperature extremes that swung hundreds of degrees depending on solar orientation. The first 2MV, one attempt launched in September 1962, but failed to escape Earth orbit when its upper stage malfunctioned, condemning another spacecraft to burn up over the Pacific after a few days of futile circling. The mission was publicly designated Sputnik 29, a meaningless label that concealed its true purpose. Soviet authorities had developed a practice of announcing failed missions as routine Cosmos satellites, a designation that served as a bureaucratic black hole where failures could be hidden. The Cosmos series eventually numbered into the thousands, mixing genuine Earth orbit missions with the wreckage of failed lunar and planetary attempts, creating a statistical fog that made it difficult for outside observers to track the true failure rate of the Soviet program. This obfuscation served multiple purposes simultaneously, concealing technological shortcomings from Cold War adversaries, preventing domestic embarrassment that might undermine political support for the space program, and maintaining the mythology of Soviet infallibility that served broader ideological objectives. The second 2MV, one launch in October 1962, finally achieved what earlier missions had failed to accomplish, escaping Earth's gravitational embrace and beginning the long coast toward Mars. This spacecraft received the public designation Mars 1, the first Soviet mission to Mars that would be officially acknowledged, though only because its initial performance suggested possible success. Mars 1 represented a genuine technological achievement, a machine built by human hands that was venturing into deep space farther than any Soviet spacecraft had traveled before, carrying instruments designed to measure the interplanetary environment and eventually observe Mars itself. The spacecraft weighed 893 kilograms, fully fueled, carried a lander capsule that would separate upon arrival, and transmitted at a frequency that could be received by the massive antennas of the Deep Space Communications Center near Yevpatoria in Crimea. The mission began well. Mars 1 sent back measurements of the solar wind, confirmed the existence of a strong radiation environment in interplanetary space, and maintained communications across ever-increasing distances as Earth and Mars both continued their orbital motion. The engineers monitoring the mission in Moscow calculated that the spacecraft would pass within 11,000 kilometers of Mars on June 19, 1963, close enough for the instruments to gather meaningful data. Close enough to declare a success even if the lander failed. But deep space proved hostile in ways that ground testing could not fully anticipate. On March 21, 1963, when Mars 1 was already 106 million kilometers from Earth, communications ceased suddenly and completely. The receiving stations tracked through their scheduled contact windows, sweeping their antennas across the predicted position of the spacecraft, amplifying their receivers to maximum sensitivity, detecting nothing but the random hiss of cosmic noise. The loss of Mars 1 occurred for reasons that can only be inferred from telemetry transmitted before the silence. Analysis of the final data suggested a failure in the spacecraft's orientation system, possibly caused by a leak in the pressurized gas system that controlled the attitude jets, or perhaps by a malfunction in the sensors that detected solar position. Without stable orientation, the spacecraft would tumble, unable to point its antenna toward Earth, unable to point its solar panels toward the sun, slowly freezing and dying in the darkness between worlds. The technical failure reflected deeper challenges in building systems reliable enough to function for months without maintenance or repair, in environments that could not be perfectly simulated on Earth, exposed to radiation levels and temperature cycles that degraded seals and electronics in unpredictable ways. Soviet engineers studied the failure carefully, implementing design changes for future missions. But the loss of Mars 1 demonstrated the immense difficulty of interplanetary exploration, the way that missions costing millions of rubles and years of work could vanish in an instant due to a single failed component. The propaganda implications of the Mars 1 failure necessitated careful management. Soviet media had announced the mission, had described its objectives in glowing terms, had prepared the public for a historic achievement. When communications were lost, the official response emphasized the mission's accomplishments during its initial months, noting the scientific data returned, carefully avoiding explicit statements about whether the spacecraft had reached Mars. Western observers assumed failure, but the ambiguity allowed Soviet authorities to avoid declaring outright defeat, to maintain the narrative of continuous progress even as the spacecraft drifted silent and dark somewhere in the asteroid belt, or beyond. This pattern of partial revelation, of emphasizing accomplishments while obscuring failures, characterized Soviet space announcements throughout the Cold War, creating a public record that bore only tangential relationship to the engineering reality experienced by the people building and flying the missions. The 2MV program continued through 1962 and 1963, with a series of attempts that added to the growing catalog of failures. Another 2MV, one launched in November 1962 but failed during the escape burn, stranding the spacecraft in Earth orbit where it was designated Sputnik 31. A 2MV, two-lander mission launched in January 1963 but suffered an upper stage failure, becoming Sputnik 33. Another 2MV, two attempt in February 1963 managed to escape Earth orbit and received the public designation Mars 2, but this mission too fell silent shortly after launch, never establishing stable communications, vanishing into the void with its lander still attached. The accumulation of failures began to create institutional stress within the Soviet space program, as political leaders demanded explanations, as design bureaus pointed fingers at manufacturing plants, as manufacturing plants blamed inadequate testing facilities, as testing facilities protested unrealistic schedules imposed by launch window constraints. The technical causes of these failures varied, but common patterns emerged. The Molniya rocket's Block L upper stage, responsible for the final push from Earth orbit to escape velocity, suffered from persistent reliability problems rooted in the difficulty of restarting rocket engines in the zero-gravity environment of orbit. The engine had to ignite, burn for a precise duration to achieve the correct velocity, then shut down cleanly without leaving residual propellant that might later cause explosions or attitude disturbances. The ignition sequence relied on complex turbopump machinery that had to spin up to thousands of revolutions per minute in seconds, feeding propellants into combustion chambers at precisely calibrated rates and pressures. Any deviation from nominal parameters could cause incomplete combustion, pressure fluctuations that damaged plumbing, or catastrophic explosions that destroyed the spacecraft before it ever left Earth orbit. The spacecraft themselves carried their own vulnerabilities. The orientation systems that maintained proper pointing required gyroscopes that could sense rotation rates, star sensors that could identify known constellations and derive absolute attitude, and sun sensors that provided a reliable reference for rough pointing. These systems had to work together, cross-checking each other, commanding the attitude control thrusters to fire in precisely timed pulses that nudged the spacecraft back toward correct orientation without overshooting and creating oscillations. The electronics controlling these systems used vacuum tubes and early transistors, components that could fail due to radiation damage, thermal stress, or simple manufacturing defects that became critical in the unforgiving environment of space. The power systems relied on solar panels that degraded over time under ultraviolet radiation, reducing their output, slowly starving the spacecraft of the electricity needed to maintain systems and communicate with Earth. By 1964, the Soviet Mars program had launched numerous missions and achieved minimal success. The political leadership's patience was eroding. The engineering teams were exhausted from repeated cycles of investigation and redesign, and the American space program was beginning to demonstrate its own capabilities with Mariner missions that successfully flew past Mars and returned high-quality images. The Soviet response involved both continued efforts using the 2MV architecture and the development of more advanced spacecraft that could carry greater instrumentation mass and incorporate lessons learned from the failures. But the next launch window in 1964 brought only more disappointment. A 2MV, 3 Venus mission launched successfully in February but suffered a communications failure shortly after launch. A 2MV, 4 spacecraft representing an evolved variant with improved systems, launched in March but failed to escape Earth orbit when its upper stage malfunctioned. Another 2MV, 4 intended for Venus, launched in April but suffered a launch vehicle failure that destroyed it during ascent. The year 1964 marked a transition in the political context surrounding the Soviet space program. Nikita Khrushchev, who had championed space achievements as proof of socialist superiority, was removed from power in October, replaced by a collective leadership that viewed space exploration with more skepticism and demanded better returns on the massive investments flowing into rocket development. The new leadership maintained support for the program, but applied greater pressure for results, creating an environment where engineers felt even more urgency to achieve success before political support evaporated entirely. This pressure coincided with preparations for new missions in the 1965 launch window, But these too encountered the curse that seemed to haunt Soviet Mars exploration. Two missions launched in November 1964, both failing to achieve escape from Earth orbit, both concealed as Cosmos satellites, both adding to the mountain of wreckage that testified to the immense difficulty of the undertaking. The pattern of failure created a kind of institutional trauma within the Soviet space program. Engineers who had devoted years to Mars missions watched their work destroyed repeatedly, sometimes in spectacular fireballs visible from the launch site, sometimes in the slower death of radio silence as spacecraft vanished into the cosmic dark. The psychological toll manifested in various ways, in the superstitions that developed around launch preparations, in the drinking that accompanied failure reviews, in the bitter humor that circulated through design bureaus where engineers joked about Mars being protected by an alien force field that destroyed Soviet spacecraft while allowing American missions to succeed. This dark comedy served as a coping mechanism for the cognitive dissonance of working in a program that proclaimed inevitable success while experiencing repeated catastrophic failure. The technological response to these failures involved incremental improvements rather than revolutionary redesigns. The spacecraft bus evolved slowly, adding redundancy to critical systems, improving thermal control through better insulation and surface coatings, enhancing communication systems with more powerful transmitters and more sensitive receivers. The Molniya rocket received modifications to improve the reliability of its upper stage, with redesigned turbopumps, improved propellant feed systems, and enhanced ignition sequences. But these changes took time to implement, time to test, time to manufacture and integrate into flight hardware, creating a lag between identifying problems and seeing fixes fly. Meanwhile, the launch windows continued their relentless astronomical cycle, opening every 26 months regardless of whether the hardware was ready, creating repeated crises where teams had to decide whether to launch vehicles with known defects or miss another opportunity. The 1969 launch window coincided with renewed Soviet determination to achieve Mars success, and with the development of significantly more capable spacecraft, designated M69. These vehicles represented a new generation of Mars probe, substantially larger than the 2MV series, carrying more comprehensive instrument suites, and designed around hard-won lessons from previous failures. The M69 spacecraft mass exceeded 5,000 kilograms, requiring the new Proton rocket for launch, a massive booster developed initially for military purposes but adapted for deep space missions. The Proton's lift capability allowed the M69 missions to carry actual Mars orbiters rather than simple flybys, spacecraft that would enter orbit around Mars and conduct extended observation campaigns spanning months, rather than brief encounters lasting hours. The engineering ambition embodied in the M69 design reflected Soviet confidence that the major technical problems had been solved, that the years of failure had taught sufficient lessons, that this new generation of hardware would finally deliver the success that had proven so elusive. The spacecraft carried cameras with much higher resolution than earlier missions, spectrometers designed to analyze the composition of the Martian surface from orbit, and instruments to measure the planet's magnetic field and radiation environment in detail. The mission architecture called for two spacecraft to launch during the 1969 window, providing redundancy and increasing the probability that at least one would succeed even if the other encountered problems. The first M69 mission launched from Baikonur on March 27, 1969, atop a Proton rocket that represented some of the most powerful launch technology in the Soviet arsenal. The Proton stood over 50 meters tall, its first stage powered by 6 engines burning unsymmetrical dimethylhydrazine and nitrogen tetroxide, hypergolic propellants that ignited on contact, eliminating the need for ignition systems, but introducing the hazard of highly toxic chemicals that required extreme care in handling. The rocket lifted off successfully, clearing the tower, beginning its pitch program to align with the desired trajectory. Then, approximately 40 seconds into flight, the payload shroud that protected the spacecraft during ascent through the atmosphere began to separate prematurely. The shroud, a streamlined fairing that enclosed the payload and reduced aerodynamic drag, was designed to jettison only after the rocket had climbed above the thick lower atmosphere. Its early separation exposed the spacecraft to aerodynamic forces for which it was never designed, forces that tore at its structure and disrupted the rocket's carefully calculated trajectory. The guidance system, detecting the sudden change in aerodynamic properties, commanded engine gimbals to adjust thrust vectors, attempting to maintain the programmed flight path. But the corrections required exceeded the authority of the gimbals, and the rocket began to deviate from its planned course, yawing and rolling as it climbed. The automatic safety system, designed to protect populated areas from falling rocket stages, detected the trajectory violation and issued a destruct command approximately 50 seconds after liftoff. The explosives embedded in the rocket's structure detonated, fragmenting the vehicle into thousands of pieces that rained down across the Kazakh steppe, scattering debris across kilometers of empty grassland. The M69 No. 1 spacecraft, which had cost years of development and represented the hopes of hundreds of engineers, disintegrated in an instant, reduced to twisted metal and shattered optics scattered among the wreckage of its launch vehicle. The investigation into the M69 No. 1 failure focused on the payload shroud separation mechanism, discovering that a sensor had provided an erroneous signal indicating that the rocket had reached sufficient altitude for fairing jettison. The sensor failure stemmed from a design flaw that had escaped detection during ground testing, a subtle interaction between vibration and electrical characteristics that manifested only under the specific conditions of powered flight. The fix was implemented quickly, too quickly perhaps, driven by the knowledge that the launch window was already open and that the second M69 spacecraft stood ready on its launch pad, waiting for clearance to fly. The decision to proceed with the second launch despite the loss of the first reflected the desperation that characterized the Soviet Mars program, the willingness to accept risk in pursuit of success, the calculation that waiting another 26 months for the next window was unacceptable when Cold War prestige hung in the balance. The second M69 mission, designated M69 No. 2, launched on April 2, 1969, just 6 days after the destruction of its predecessor. The Proton rocket performed flawlessly through first-stage burnout and separation, through second-stage ignition and burn, through the jettison of the payload shroud at the correct altitude. The third stage ignited as planned, pushing the spacecraft toward the velocity needed to escape Earth's gravity. Then, approximately 438 seconds after liftoff, telemetry from the rocket ceased abruptly. Ground controllers watched their displays go blank, listened to their speakers fall silent, and knew immediately that something catastrophic had occurred. Later analysis of fragmented telemetry suggested that the third stage had suffered a structural failure, possibly due to propellant sloshing that created unexpected loads, possibly due to a manufacturing defect in the propellant tank walls, possibly due to resonance between the structure and engine vibrations that amplified until something broke. The precise cause remained uncertain, buried in the debris that fell into the Pacific Ocean. But the result was definitive. Another spacecraft destroyed, another multi-million ruble investment vaporized, another failure to add to the catalog. The loss of both M69 missions within days represented a particular kind of disaster for the Soviet Mars program. The failures had consumed the entire 1969 launch window, had destroyed two of the most sophisticated planetary spacecraft ever built by the Soviet Union, and had occurred at a time when American Apollo missions were preparing to land humans on the moon, shifting global attention toward a triumph of space exploration that would make Soviet achievements seem diminished by comparison. The political implications reverberated through the space program's bureaucracy, triggering investigations, personnel changes, and a fundamental reassessment of whether the Mars program justified its costs and risks. Yet the program continued, driven partly by institutional momentum, partly by the genuine scientific interest in Mars that motivated many of the engineers and scientists involved, and partly by the calculation that abandoning Mars exploration would represent a concession of defeat to the Americans that was psychologically and politically unacceptable. The design bureaus began developing the next generation of Mars hardware, even as they were still analyzing the M69 failures, preparing for the 1971 launch window that would offer another opportunity. The new missions, designated simply Mars 2 through Mars 5, incorporated additional improvements, reflected growing sophistication in Soviet deep space technology, and carried the accumulated weight of all the previous failures, all the political pressure, all the institutional hope that this time would be different. The 1971 missions represented the most ambitious Soviet Mars exploration effort to date. The spacecraft design evolved from the M69 architecture, but added complexity and capability in multiple dimensions. Each spacecraft consisted of an orbiter that would enter Mars orbit and conduct long-term observations, and a lander that would separate during approach and descend to the Martian surface. The lander design incorporated Soviet experience from the Luna program of lunar missions, adapting technologies proven on the Moon for the different challenges of Mars. The Martian atmosphere, though thin compared to Earth's, was thick enough to require heat shields and parachutes for descent, necessitating a landing sequence far more complex than the purely rocket-powered descents used on the airless Moon. The Mars landers, carried by the 1971 missions, represented mechanical marvels of their era. Each lander was encased in a spherical aeroshell that would protect it during the violent deceleration as it plunged into the Martian atmosphere at over 5 kilometers per second. The heat shield material had to withstand temperatures exceeding 2,000 degrees Celsius as friction converted kinetic energy into heat, had to ablate in controlled fashion to carry that heat away from the spacecraft structure, had to maintain integrity until atmospheric density had slowed the lander to velocities where parachutes could deploy safely. The parachute system itself represented a technical challenge because the thin Martian atmosphere provided less drag than the dense air of Earth, requiring larger parachutes and more robust deployment mechanisms to ensure reliable operation. Beneath the heat shield and parachute, the lander contained instruments designed to analyze Martian soil, photograph the surface, measure atmospheric composition and meteorological conditions, and search for signs of life through experiments that would test soil samples for biological activity. The design included a sophisticated radio system that would transmit data to the orbiting spacecraft, which would then relay it to Earth during scheduled communication windows. The entire landing sequence, from atmospheric entry to surface touchdown, would last approximately 15 minutes, during which the spacecraft would be entirely autonomous, executing commands programmed before launch, adapting to conditions using onboard sensors and simple computers, with no possibility of ground intervention due to the time delay for radio signals traveling between Earth and Mars. Perhaps most remarkably, each 1971 lander carried a small rover designated Prop M, a roving vehicle that represented one of the first attempts to create a mobile robot for planetary exploration. The Prop M rover weighed only 4.5 kilograms, was designed to move on 2 skis connected by a tether to the lander, and carried instruments to measure soil density as it traveled. The rover's range was severely limited by its tether to approximately 15 meters, but within that radius it would provide information about surface conditions away from the lander's immediate vicinity, testing technologies that might enable more ambitious rover missions in the future. The engineering that went into this small device reflected the same ambition that characterized the entire Soviet Mars program, the drive to accomplish firsts even when the technical challenges seemed overwhelming, the willingness to attempt missions at the edge of feasibility rather than waiting for perfect solutions. The Mars 2 mission launched on May 19, 1971, beginning a journey that would take nearly 6 months and cover more than 400 million kilometers. The Proton rocket performed flawlessly, delivering the spacecraft into Earth parking orbit, then executing the escape burn that sent it arcing away from Earth toward its intercept with Mars. The spacecraft settled into the coast phase of flight, spinning slowly to maintain thermal stability, its systems powered by solar panels that tracked the sun, its instruments largely dormant to conserve power during the long months of transit. Ground controllers monitored the spacecraft daily, checking system health, making small trajectory corrections using the onboard propulsion system, uploading commands for upcoming maneuvers. 9 days after Mars 2 launched, Mars 3 lifted off, following an essentially identical trajectory, timed to arrive at Mars just days after its twin. The launch of 2 missions so close together provided redundancy and increased the probability of success. But it also created operational complexity, as ground controllers had to manage 2 spacecraft simultaneously, scheduling communication sessions, calculating trajectory corrections, preparing commands for both missions while ensuring that instructions intended for one spacecraft were not accidentally transmitted to the other. The operational burden was substantial, requiring multiple shifts of controllers working around the clock, coordinating with tracking stations spread across Soviet territory to maintain contact with spacecraft that were visible from different locations as Earth rotated. The transit to Mars tested spacecraft systems in ways that ground testing could not fully replicate. The solar panels gradually degraded under ultraviolet radiation and micrometeorite impacts, reducing power generation capacity. Electronics components aged under constant operation, with critical systems like the radio transmitter showing subtle changes in performance. The navigation team tracked the spacecraft using radio ranging and Doppler shift measurements, building an increasingly accurate picture of the trajectory, calculating the small velocity changes needed to target the desired arrival conditions at Mars. These trajectory correction maneuvers required firing the spacecraft's propulsion system for carefully calibrated durations, using precious fuel that could not be replenished, making decisions that balanced the desire for optimal arrival conditions against the need to conserve propellant for later maneuvers. As the spacecraft approached Mars in November 1971, they encountered a planet in crisis. A global dust storm had begun in September and had grown to envelop the entire planet by the time the Soviet missions arrived. Ground-based telescopes, which normally could observe dark and bright features on Mars corresponding to regions of different albedo, saw only a featureless orange disk obscured by atmospheric dust. The storm represented a natural Martian phenomenon, occurring every few years when conditions aligned to lift dust from the surface into the thin atmosphere, where it could remain suspended for weeks or months, gradually settling back down as the storm dissipated. For the Soviet missions, the dust storm created hazardous conditions that would challenge every aspect of their operations. Mars 2 reached Mars on November 27, 1971, executing its arrival sequence as planned. The spacecraft oriented itself correctly, ignited its main engine to slow down and allow Martian gravity to capture it into orbit, then shut down the engine after the calculated burn duration. Prior to the orbit insertion burn, the lander had separated, beginning its independent approach to the surface. The lander, however, encountered the dust storm during its descent. The precise sequence of events during those 15 minutes of terror as the lander plunged into the Martian atmosphere can only be inferred from incomplete telemetry and later analysis. The entry angle appears to have been too steep, causing deceleration forces higher than the spacecraft was designed to withstand. The heat shield performed its function, protecting the lander from thermal destruction, but the parachute deployment sequence may have been disrupted by the violent entry. The lander impacted the Martian surface at high velocity, too fast for survival, becoming the first human-made object to touch the surface of Mars, but at the cost of complete destruction. The Soviet Union announced that Mars 2 had delivered a pennant bearing the Soviet coat of arms to the Martian surface, marking the achievement of landing a human artifact on another planet, carefully framing the narrative to emphasize the accomplishment while obscuring the fact that the lander had crashed rather than landing softly as intended. This parsing of language typified Soviet space announcements, where failures could be reinterpreted as partial successes, where objectives could be revised retrospectively to match outcomes, where the public narrative diverged from engineering reality. The Mars 2 orbiter, however, survived its arrival and began the scientific mission for which it had been designed, photographing Mars from orbit, measuring atmospheric parameters, collecting data that would be stored on tape recorders and transmitted to Earth during communication windows. Mars 3 arrived on December 2, 1971, just 5 days after its sister ship. The approach sequence mirrored that of Mars 2, with the lander separating before the orbiter's insertion burn. But this time, the landing sequence performed better, or perhaps simply encountered slightly less hostile conditions as it descended through the dust-choked atmosphere. The lander survived entry, deployed its parachute successfully, jettisoned its heat shield, and ignited its terminal descent engines to slow the final approach to the surface. At an altitude of approximately 20 meters, the lander engines shut down, allowing it to fall the remaining distance to a touchdown that was hard but survivable. The pedals that had protected the lander during descent opened, exposing the instruments to the Martian environment. The landing occurred at 45 degrees south latitude in a region that Western astronomers called Ptolemaeus Crater, though Soviet sources used different nomenclature based on their own mapping conventions. For 90 seconds, Mars 3 transmitted data from the Martian surface. The signal was weak, subject to noise and interference, but it was unmistakably there. proof that the lander had survived touchdown and was attempting to execute its surface mission. Then, abruptly, transmission ceased. The orbiter continued to listen during its scheduled relay window, its receivers tuned to the lander's frequency, detecting nothing but silence. Ground controllers commanded the orbiter to try again during subsequent passes over the landing site, maintaining hope that perhaps the lander's transmitter had overheated or that some intermittent problem might resolve itself. But Mars 3 never transmitted again. The 90 seconds of data it had sent proved insufficient for meaningful analysis. No images were received, no soil measurements, no meteorological data, nothing but carrier signal confirming that the lander had briefly functioned before falling silent. The failure of Mars 3 to sustain surface operations devastated the mission team. They had succeeded in achieving the first soft landing on Mars, an accomplishment that deserved celebration, but the loss of the science mission represented a bitter disappointment that overshadowed the technical achievement. Analysis suggested multiple possible explanations for the brief operational lifetime. The dust storm may have covered the solar panels too quickly, starving the lander of power. The landing may have been rougher than telemetry suggested, causing internal damage that manifested after initial systems checks. An electrical short could have disabled power systems. The antenna might have shifted position during landing, breaking the radio link with the orbiter. The exact cause remained uncertain, but the outcome was clear. The most sophisticated Soviet Mars lander yet built had transmitted for less time than it took to read this sentence before vanishing into history. The Prop M rover aboard Mars 3, designed to conduct the first mobile exploration of the Martian surface, never deployed. The rover remained attached to its dead lander, its skis that should have left tracks in Martian soil instead sitting motionless, its instruments that should have measured density and composition instead silent and dark. The rover represented dreams of exploration that exceeded even the ambitious goals of landing, represented plans for mobile science that would have fundamentally changed the nature of Mars exploration had they succeeded. Instead, Prop M became a memorial to potential unrealized, a machine built with care and ingenuity that never got the chance to execute its mission. Somewhere on Mars, in the region around Ptolemaeus Crater, the Mars 3 lander and its cargo of instruments and rover rest beneath dust that may have accumulated over decades. Unvisited, unverified, their precise location uncertain to within kilometers, because the brief transmission provided insufficient data for precise position determination. The Mars 2 and 3 orbiters continued operating for months after the landing attempts, executing their programmed observation sequences, photographing the planet as the dust storm gradually cleared, measuring atmospheric composition and temperature profiles, detecting weak magnetic fields, gathering data that contributed to humanity's understanding of Mars even as the loss of the landers diminished the overall success of the missions. The orbiters demonstrated that Soviet deep space technology had matured significantly, that spacecraft could survive the rigors of interplanetary transit and operate reliably in Martian orbit, that the fundamental technologies of planetary exploration had been mastered even if the more challenging task of landing remained elusive. The political reception of the 1971 missions reflected the ambiguity of their outcomes. Soviet media announced the achievements, the delivery of instruments to the surface, the operation of orbiters, but did so in muted fashion that suggested recognition of the incomplete nature of the success. Western space agencies and scientific communities acknowledged the technical accomplishments while noting the failures, recognizing that the Soviet Union had achieved firsts in reaching the Martian surface, even if the science return fell far short of mission objectives. The American Mariner 9 mission, which arrived at Mars shortly after the Soviet spacecraft, and which also encountered the global dust storm, demonstrated superior performance in its orbital mission, returning high-quality images once the storm cleared, and conducting science operations that exceeded anything the Soviet orbiters achieved. This comparative performance reinforced the perception that American space technology had surpassed Soviet capabilities, a perception that the Soviet leadership found galling, but increasingly difficult to refute. Two additional spacecraft, Mars 4 and Mars 5, launched during the 1973 window, attempting to build on the mixed results of the 1971 missions. Mars 4 suffered a computer malfunction that prevented it from entering Mars orbit, instead executing a flyby that returned limited data before continuing into heliocentric orbit. Mars 5 successfully entered orbit and operated for several weeks before succumbing to what appears to have been a propellant leak that caused it to lose attitude control and cease operations. Neither mission attempted surface landings, representing a retreat from the ambitious goals of 1971 to more conservative objectives focused on reliable orbital operations. The reduced scope reflected both the technical challenges revealed by earlier landing attempts and the declining political support for Mars exploration as Soviet leadership redirected resources toward other priorities, including military programs and the development of space stations in Earth orbit. The broader context of Soviet Mars exploration includes the parallel programs that competed for resources and attention throughout the same period. The Luna program of lunar missions achieved greater success than Mars efforts, successfully landing multiple spacecraft on the Moon, returning samples robotically, and deploying the Lunokhod rovers that demonstrated mobile robotic exploration. The Venera program targeting Venus also achieved greater success than Mars missions, with landers that survived the hellish surface conditions of Venus long enough to transmit images and measurements. The relative success of Luna and Venera missions compared to Mars attempts reflected both the specific technical challenges of each target and the accumulated experience that comes from sustained focus. Mars missions always competed for priority with these other programs, often losing out when resources became scarce or when political leaders demanded success stories that Mars seemed unable to provide. The engineering lessons from the Soviet Mars program influenced planetary exploration globally. The challenges of interplanetary navigation, of spacecraft autonomy during critical events, of building systems reliable enough to function after months in deep space, of designing entry systems that could survive atmospheric entry, of creating instruments that could operate in alien environments. All these problems had to be solved through iterative design and painful failures that revealed what did not work. Soviet engineers developed expertise in heat shield design, parachute dynamics in thin atmospheres, autonomous landing sequences, and orbital relay communications that informed later missions. The institutional knowledge accumulated through repeated attempts, through failure analysis, through the gradual refinement of designs, represented a costly education purchased with destroyed hardware and missed opportunities. The classification and secrecy that surrounded the Soviet Mars program created historical distortions that persist decades after the missions flew. Many failures were never officially acknowledged, existing only as gaps in launch records or as suspicious Cosmos satellite designations that Western analysts suspected masked planetary attempts. Documentation from the program remained scattered and incomplete, with some records destroyed intentionally as part of routine classification protocols, others lost during the chaos following the Soviet Union's collapse, still others buried in archives that have never been fully cataloged or opened to researchers. Engineers who worked on the missions have written memoirs and given interviews that provide fragments of the story. But memory is fallible, and political considerations sometimes color recollections. Physical hardware that survived in museums or storage facilities offers tangible evidence, but without documentation, the interpretation of that hardware remains uncertain. The reconstructed history of Soviet Mars exploration relies on multiple sources that must be cross-referenced and evaluated critically. Western intelligence agencies tracked Soviet launches using radar and optical systems, detecting when rockets left their paths and tracking debris from failures, but these observations captured only the gross features of missions and could not determine payloads or mission objectives with certainty. Radio amateurs and professional astronomers listened for signals from Soviet spacecraft, sometimes detecting transmissions that revealed the existence of missions not publicly announced. Soviet scientific publications occasionally included references to data from specific missions, providing clues about what had flown and what it had measured. The Soviet space program included many participants from fraternal socialist countries, and some of these foreign engineers later spoke more freely about their experiences than their Soviet counterparts felt able to do. Synthesis of these disparate sources produces a history that is more complete than official Soviet records alone would suggest, but still fragmentary, still uncertain in many details, still subject to revision as new information emerges. The scientific legacy of the Soviet Mars missions extends beyond the specific data they returned. The orbiters photographed the Martian surface at resolutions that, while modest by later standards, revealed features that shaped understanding of the planet's geology and history. Images showed evidence of past water flows in the form of channels and valleys, suggesting that Mars had once possessed a thicker atmosphere and warmer climate capable of supporting liquid water on its surface. Measurements of atmospheric composition confirmed that Mars's thin atmosphere consists primarily of carbon dioxide, with trace amounts of nitrogen, argon, and water vapor, creating surface pressures less than 1% of Earth's atmosphere. Temperature measurements revealed extreme variations, with equatorial regions warming above freezing during summer days, but plunging far below freezing at night and during winter, creating thermal stresses that contributed to surface weathering. The discovery of weak magnetic fields around Mars surprised scientists who had expected a dead planetary core incapable of generating magnetism. The fields detected by Soviet orbiters appeared to be localized rather than global, suggesting either remnant magnetism frozen into ancient rocks from an era when Mars possessed a global magnetic field, or some other mechanism for generating small-scale magnetic features. This finding influenced theories about Mars's internal structure and thermal evolution, suggesting a history more complex than simple models of progressive cooling and solidification. The magnetic measurements also had implications for understanding how the solar wind interacts with Mars's atmosphere, potentially contributing to atmospheric erosion over geological timescales. The technology developed for Soviet Mars missions found applications in other space programs. The Proton rocket that launched most Mars missions became a workhorse of the Soviet and later Russian space program, launching space station modules, communications satellites, and various other payloads. The spacecraft bus designs evolved into variants used for missions to Venus, to comets, and for Earth orbit applications. The heat shield materials and parachute technologies developed for Mars landers influenced Soviet entry vehicle design across multiple applications. The deep space communication systems tested on Mars missions informed the development of communication networks used for subsequent deep space exploration. Even failed missions contributed to the technological base, revealing problems that could be fixed, demonstrating approaches that needed refinement, gradually building the engineering knowledge required for reliable spaceflight. The human dimension of the Soviet Mars program deserves attention equal to the technical history. Thousands of engineers, technicians, scientists, and support personnel devoted years of their lives to Mars exploration, working long hours in difficult conditions, accepting restrictions on travel and communication due to security classifications, investing emotional energy in missions that often ended in failure. The culture of Soviet design bureaus combined genuine technical brilliance with bureaucratic dysfunction, ideological orthodoxy with pragmatic problem-solving, commitment to collective goals with personal ambitions for recognition and advancement. Engineers worked in teams that could accomplish remarkable feats when properly coordinated, but that also suffered from organizational pathologies including poor communication between groups, competition for resources that undermined collaboration, and political pressures that distorted technical decision-making. The chief designers who led Soviet space programs operated under pressures that Western engineers rarely experienced. These leaders bore personal responsibility for mission outcomes, faced political consequences for failures, and had to navigate complex relationships with military customers, political overseers, and rival design bureaus. Sergei Korolev, who led early Soviet space efforts including initial Mars missions, died in 1966 following surgery complications, his health undermined by years of overwork and stress, including time spent in Stalin's Gulag during the 1930s. His successors inherited programs that had grown enormously complex, that attempted objectives at the edge of technical feasibility, and that operated under political expectations that often exceeded realistic capabilities. The role of chief designer combined technical leadership with political acumen, requiring individuals who could inspire their teams while satisfying political masters, who could make hard technical decisions while managing scarce resources, who could maintain optimism in the face of repeated failures while learning from mistakes. The rank-and-file engineers who designed spacecraft components, calculated trajectories, wrote computer programs, tested systems, and monitored missions experienced the program at a different level, but with no less intensity. These individuals often worked in closed cities, specially designated locations where sensitive work occurred under enhanced security, where residents needed special permits to enter or leave, where contact with foreigners was forbidden, and sometimes even communication with relatives living elsewhere in the Soviet Union was restricted. Life in closed cities offered certain advantages, including better housing and food supplies than generally available in the Soviet Union, but at the cost of isolation and constant surveillance by security services. Engineers in these environments developed tight-knit professional communities, forming relationships that persisted across decades, creating networks of mutual support that helped individuals navigate the challenges of their work and living conditions. The technical documentation produced by Soviet Mars programs reveals engineering approaches that sometimes diverged from Western practices. Soviet designers often favored robust, relatively simple systems that could tolerate failures of individual components, building redundancy into designs, and accepting performance penalties in exchange for reliability. This philosophy reflected partly the limitations of Soviet electronics and manufacturing, which lagged behind Western capabilities in miniaturization and precision, but excelled in ruggedized designs suited for harsh environments. The emphasis on redundancy and simplicity conflicted at times with the ambitious objectives of Mars missions, which pushed the boundaries of what simple, robust systems could accomplish, creating tension between conservative engineering and the need for advanced capabilities. Soviet spacecraft typically used analog control systems based on operational amplifiers and discrete components rather than the digital computers that increasingly dominated Western spacecraft design during the 1960s and 1970s. This choice reflected both technological constraints and design philosophy, with analog systems offering certain advantages in radiation tolerance and real-time response at the cost of flexibility and complexity. When digital computers were incorporated into Soviet spacecraft, they tended to be specialized processors designed for specific functions rather than general-purpose computers running software. The programming for these specialized processors occurred at a very low level, often with machine code or simple assembly language, requiring programmers who understood hardware intimately and who could optimize their code to execute within tight constraints on memory and processing speed. The ground control systems for Soviet Mars missions centered on the Deep Space Communications Center near Yevpatoria in Crimea, where massive dish antennas tracked spacecraft across the sky, transmitting commands and receiving telemetry. The facility operated continuously, with multiple shifts of controllers and engineers monitoring missions, coordinating with ballistics teams who calculated trajectories, with spacecraft designers who interpreted telemetry and diagnosed problems, with scientific teams who planned observations and analyzed data. The communication links to Mars operated at very low data rates by modern standards, often just tens or hundreds of bits per second, limited by the power available for spacecraft transmitters, the size of spacecraft antennas, the sensitivity of ground receivers, and the immense distances involved. A radio signal traveling from Mars to Earth required between 4 and 21 minutes depending on the relative positions of the planets in their orbits, creating time delays that prevented real-time interaction and required careful planning of all spacecraft activities. The data transmitted from Mars missions traveled through relay stations and processing centers before reaching the scientists who would analyze it. Telemetry received at tracking stations was recorded on magnetic tape, then transported physically to data centers where it would be processed to extract instrument readings, spacecraft health information, and scientific measurements. Images captured on film aboard spacecraft had to be scanned and transmitted as sequences of brightness values, then reconstructed on the ground using specialized equipment that could print photographic images from the digital data. This entire chain of data handling introduced opportunities for errors, degradation, and loss, with the fidelity of the final science data depending on the integrity of systems and processes at every stage. The limitations of data handling technology constrained what missions could accomplish, forcing choices about which data to transmit immediately and which to store on onboard recorders for later playback, which images to prioritize, and which to defer or skip entirely. The scientific objectives of Soviet Mars missions evolved as understanding of Mars itself evolved. Early missions targeted basic questions about the planet's mass, orbit, and surface properties, seeking to confirm or refute various theories about Martian conditions. As data accumulated from both Soviet and American missions, the questions became more sophisticated, focusing on atmospheric chemistry, surface geology, the history of water, and eventually the possibility of life. Soviet instrument packages typically included cameras for imaging, spectrometers for analyzing light reflected from or emitted by Mars, magnetometers for measuring magnetic fields, and radiation detectors for characterizing the particle environment. Landers added sensors for atmospheric pressure, temperature, and humidity, cameras for direct surface imaging, and experiments designed to detect biological activity in soil samples. The search for life on Mars represented one of the most compelling drivers for Mars exploration, capturing public imagination and justifying the enormous costs of planetary missions. Scientists designing biological experiments faced fundamental challenges. Life detection instruments had to operate autonomously, executing complex procedures without human intervention, testing for signatures of metabolism or reproduction that might be recognized as biological, even if Martian life was fundamentally different from terrestrial organisms. The experiments flown on Soviet landers included simple tests where soil samples would be mixed with nutrients and monitored for signs of gas exchange or other chemical changes that might indicate biological activity. The design of these experiments provoked debates about what exactly would constitute evidence of life, about whether the tests could distinguish biological from non-biological chemistry, about whether the harsh Martian surface conditions might preclude life even if the planet harbored organisms in more protected environments below ground, or in the past, when conditions were more favorable. The question of life on Mars intertwined with broader questions about planetary habitability and the prevalence of life in the universe. If Mars, a planet sharing the same solar system as Earth and possessing at least some potentially habitable conditions in its past, harbored life, then the implication would be that life arises readily wherever conditions permit, suggesting that the universe might be teeming with organisms. Conversely, if Mars proved definitively lifeless despite past conditions that seemed favorable, that would suggest life is rare, dependent on specific circumstances that perhaps only Earth enjoyed. The stakes extended beyond scientific curiosity into philosophical territory, touching on humanity's place in the cosmos, on whether we are alone or part of a broader community of living worlds. The environmental conditions on Mars present formidable challenges to life as we understand it. The thin atmosphere provides little protection from ultraviolet radiation and cosmic rays, both of which damage biological molecules and make the surface hazardous to unprotected organisms. The extreme cold during Martian nights and winters would freeze water, disrupting cellular processes that depend on liquid aqueous environments. The absence of liquid water on the surface today, due to the low atmospheric pressure and low temperatures, eliminates what is considered the fundamental requirement for life. However, evidence from various missions suggests that subsurface environments might be more hospitable, with possible liquid water aquifers protected from radiation and experiencing more stable temperatures. The discovery of subsurface ice at moderate depths opened possibilities for life existing in these protected zones, using chemical energy from rock-water interactions rather than relying on photosynthesis. Soviet Mars missions contributed pieces to this puzzle through their measurements of atmospheric composition, surface chemistry, and environmental conditions. The detection of water vapor in the atmosphere, even in small amounts, confirmed that water existed somewhere on Mars in some form. The observation of polar ice caps that advanced and retreated with seasons demonstrated that water ice and carbon dioxide ice cycled through the Martian climate system. The measurements of soil composition from landers that transmitted briefly before failing provided snapshots of surface chemistry, revealing high concentrations of iron oxides that gave Mars its distinctive red color. Detecting perchlorates and other salts that would depress the freezing point of water and potentially allow brines to exist as liquids at temperatures below the normal freezing point. The evidence for past water on Mars accumulated through observations of surface features that resembled terrestrial formations created by flowing water. Valley networks that branched like river systems suggested rainfall or groundwater seepage carving channels through Martian rock. Layered sediments visible in crater walls appeared consistent with deposition by water over time. Ancient shorelines suggested that Mars might once have possessed oceans or large lakes that later dried up as the climate changed. These observations pointed toward a very different Mars in the distant past. A planet with a thicker atmosphere capable of maintaining higher temperatures and pressure. a hydrological cycle with rain and runoff, possibly conditions suitable for life that later deteriorated as the planet lost its atmosphere through some combination of solar wind stripping and chemical reactions with surface rocks. The mechanism by which Mars lost its atmosphere became a subject of intense research, with implications for understanding planetary evolution and habitability. The lack of a strong global magnetic field left Mars's atmosphere exposed to the solar wind, streams of charged particles flowing outward from the Sun, that could strip away atmospheric molecules over geological time. The cold temperatures at Mars's greater distance from the Sun caused atmospheric gases to condense and freeze, falling to the surface and becoming trapped in ice or reacting with rocks. The lower gravity of Mars, being only about 38% of Earth's surface gravity, made it easier for atmospheric molecules to escape to space when energized by solar ultraviolet radiation. These processes, operating over billions of years, could transform a planet from potentially habitable to the cold, dry, radiation-bathed desert observed today. The implications of this transformation extend to considerations of terraforming, the hypothetical process of deliberately modifying Mars to make it more Earth-like and habitable for humans. If Mars once possessed thick atmosphere and liquid water, then perhaps those conditions could be restored through technological intervention, releasing greenhouse gases to warm the planet, melting ice to fill lakes and rivers, allowing vegetation to take root and produce oxygen through photosynthesis. The concept of terraforming Mars moved from science fiction to serious scientific discussion, as Mars exploration revealed both the planet's harsh current state and evidence of its more hospitable past. The technical challenges of terraforming would be immense, requiring energy and material resources on planetary scales, timescales spanning centuries or millennia, and solutions to problems like the ongoing atmospheric loss processes that made Mars inhospitable in the first place. Soviet documents and discussions occasionally referenced long-term visions of Mars colonization, though these remained largely aspirational rather than programmatic. The practical requirements for sustaining human presence on Mars include reliable transportation between Earth and Mars, life support systems that can function for years in isolated environments, protection from radiation, food production using Martian resources, extraction of water from ice or hydrated minerals, production of fuel and oxygen from atmospheric CO2, and psychological support for crews living far from Earth in confined conditions. Each of these requirements presents technical challenges that remain incompletely solved decades after the Soviet Mars program flew its missions, though progress continues through research conducted in analog environments on Earth, through development of advanced life support systems for space stations, and through planning for eventual crewed missions to Mars. The Soviet Mars program operated during an era when human Mars missions seemed potentially imminent, when some planners envisioned crews traveling to Mars as a natural follow-on to lunar exploration. These visions dissipated as the costs and complexities became clearer, as political priorities shifted, as the technical challenges of long-duration spaceflight emerged through experience with space stations in Earth orbit. The transition from robotic exploration to human presence involves not just scaling up existing technologies, but solving qualitatively different problems around reliability, safety, and return capability. A robotic mission that fails can be written off as unfortunate but acceptable loss. A crewed mission that fails means dead astronauts and political catastrophe. This asymmetry drives very different design philosophies and risk acceptance, making crewed missions far more expensive and complex than robotic precursors. The economic context of Soviet Mars exploration involved resource allocation within a centrally planned economy that operated on principles fundamentally different from market economies. The Soviet space program received funding through state budgets allocated by political decisions rather than market forces, competing for resources with military programs, industrial development, consumer goods production, and other state priorities. The exact budgets for Mars missions remain unclear, buried in classified documents, and obscured by the accounting practices of the Soviet economy, where prices did not necessarily reflect market values, and where comparisons with Western currencies require assumptions about exchange rates that vary depending on what was being measured. What is clear is that the Mars program consumed substantial resources over more than a decade, resources that produced limited returns in terms of scientific data and technological capabilities relative to the investments, particularly when compared with the more successful Luna and Venera programs. The question of whether the Soviet Mars program should be judged a failure or partial success depends on the metrics used for evaluation. By the standards of achieving stated mission objectives, landing functioning spacecraft on Mars and conducting extensive surface operations, the program largely failed, with only brief transmissions from Mars 3 to show for multiple landing attempts. By the standards of advancing technological capabilities and contributing to scientific understanding of Mars, the program achieved more, developing deep space technologies, returning orbital data, and demonstrating that Mars landing was possible even if reliable operations remained elusive. By the standards of Cold War competition, the program produced mixed results, achieving some firsts, including the first object on the Martian surface, but being overshadowed by American successes that garnered more international recognition and produced higher quality science returns. The legacy of Soviet Mars exploration includes both direct contributions to planetary science and more subtle influences on the evolution of space exploration. The hardware designed for Soviet missions had informed later spacecraft design across the international community. The operational procedures developed for managing deep space missions influenced how missions are planned and executed. The failures experienced by Soviet missions revealed problems that other space agencies could learn from, contributing to the collective understanding of what makes planetary exploration difficult. The institutional structures created to support Mars exploration persisted beyond the Soviet Union's collapse, with many of the same design bureaus and facilities continuing to function as part of Russia's space program, maintaining continuity of expertise across political transformations. The individuals who devoted their careers to Soviet Mars exploration carried their experiences forward in various ways. Some continued working in the Russian space program after the Soviet Union's end, contributing to missions like Mars 96, which itself failed during launch in 1996, adding another chapter to the saga of Russian Mars mission difficulties. Others emigrated to Western countries, bringing their expertise to international space programs, contributing to missions run by NASA, ESA, and other agencies. Still others retired from spacework, carrying memories of the missions they had built and operated, occasionally sharing their stories with historians and journalists who sought to reconstruct the classified history of Soviet space achievements and failures. The process of historical reconstruction itself represents a challenge, as documentation gaps and continuing classification restrictions limit access to primary sources. Russian space archives have opened partially since the Soviet era, allowing researchers to examine some documents that were previously inaccessible, but many records remain classified or lost. The individuals who participated in the programs are aging and passing away, taking their memories with them, creating urgency for oral history projects that can capture their recollections before that knowledge is lost. The physical hardware that survives in museums and storage facilities provides tangible evidence that can be studied, photographed, measured, and analyzed, offering insights that documents cannot fully convey about how systems were actually built and integrated. The technical analysis of surviving hardware reveals details about Soviet manufacturing capabilities and engineering practices. The quality of machining, welding, and assembly can be assessed through direct examination. The choice of materials, the design of structural elements, the routing of cables and plumbing, the integration of components, all these physical realities speak to how Soviet engineers solved problems and made trade-offs. Comparisons with Western spacecraft of the same era reveal both similarities and differences in approach, with Soviet designs generally favoring heavier construction, more conservative electronics, and simpler system architectures, while Western designs push toward lighter weight, more advanced computing, and greater complexity in service of capability. The scientific instruments carried on Soviet Mars missions reflected the capabilities of Soviet science and technology in areas like optics, spectroscopy, particle detection, and sensor design. Soviet scientists made important contributions to space physics and planetary science, despite working with equipment that sometimes lagged Western capabilities in areas like sensitivity and resolution. The constraints imposed by available technology drove creative approaches to instrument design, finding ways to extract meaningful data from simple sensors, using clever techniques to maximize information return within the limitations of available telemetry bandwidth and spacecraft power budgets. The scientific publications that resulted from Soviet Mars missions contributed to the international body of knowledge about Mars, though language barriers and publication practices sometimes limited the dissemination of Soviet findings to Western scientists. The international scientific community's response to Soviet Mars missions combined professional interest in the results with skepticism about the claims made in Soviet announcements. Western scientists recognized that political pressures influenced how Soviet achievements were portrayed, that mission failures were concealed or minimized, that the data released publicly might represent only the most favorable results. This skepticism was justified by the pattern of Soviet announcements that emphasized successes while being silent about failures, that made claims of firsts even when the technical accomplishments were marginal, that sometimes contradicted evidence available from other sources. At the same time, Western scientists recognized genuine achievements when they occurred, acknowledging that the challenges of Mars exploration were immense regardless of who attempted them, that failures were inevitable and nothing to be ashamed of in the context of such ambitious exploration. The relationship between the Soviet and American Mars programs involved both competition and indirect cooperation. The competition drove both programs forward, creating pressure to achieve firsts and demonstrate capability, accelerating the pace of exploration beyond what might have occurred absent Cold War rivalry. The indirect cooperation occurred through the sharing of scientific results at international conferences, through the publication of findings in peer-reviewed journals that crossed political boundaries, and through the way that each program learned from the other's successes and failures, even when direct collaboration was prohibited by political considerations. This complex relationship of competitive cooperation characterized much of the space age, where rival nations raced to achieve milestones while simultaneously contributing to a collective understanding of space that transcended political divisions. The Soviet Mars program's role in Cold War propaganda extended beyond specific mission announcements to shape broader narratives about technological progress and social systems. Soviet ideology claimed that socialist planning would outperform capitalist chaos, that collective action directed by scientific principles would achieve results impossible for individualistic competition. Space achievements served as tangible evidence for these claims, visible demonstrations that could be broadcast globally, impressing audiences in developing countries that were choosing between Soviet and American models of development. Mars missions, when they succeeded even partially, reinforced the narrative of Soviet technological prowess. But the failures, when they leaked into public awareness, undermined these claims, suggesting that perhaps Soviet systems were not as superior as propaganda claimed. The collapse of the Soviet Union in 1991 transformed the context in which Soviet Mars missions were understood. Information that had been closely guarded became accessible, sometimes through chaotic leaks as institutional controls broke down, sometimes through more orderly archival openings as new governments adopted different policies toward historical transparency. The economic crisis that accompanied the Soviet collapse devastated the Russian space program, slashing budgets, causing expertise to drain away as engineers left for better-paying opportunities, leaving facilities to deteriorate. Mars exploration became impossible under these conditions, with Russia unable to mount new missions even as American and European programs continued to advance. The Mars 96 mission represented a brief resurgence of Russian Mars ambitions, an ambitious mission carrying extensive international payloads. But its failure during launch seemed to confirm that the curse haunting Russian Mars exploration persisted beyond the political system that had originally fostered it. The scientific questions that motivated Soviet Mars missions continue to drive exploration today, with new missions building on the foundation laid by early pioneers. The search for life, the understanding of Mars's climate history, the characterization of resources that could support future human missions. These objectives that Soviet engineers pursued in the 1960s and 1970s remain central to current Mars exploration programs. The technologies have advanced enormously, with modern spacecraft carrying high-resolution cameras, sophisticated spectrometers, and capable computers that make Soviet-era systems seem primitive. But the fundamental challenges remain: the difficulty of landing safely on Mars, the complexity of operating autonomously at vast distances from Earth, the need for reliability in hostile environments, the limitations imposed by mass and power constraints. Modern Mars missions benefit from lessons learned during the Soviet program and subsequent exploration by many nations. The understanding of Martian atmospheric dynamics informs the design of entry systems. Knowledge of surface conditions shapes the engineering of landers and rovers. Experience with communication systems and operational procedures makes mission management more effective. The accumulation of negative knowledge, understanding what doesn't work, proves as valuable as positive results, preventing repetition of past mistakes. Soviet failures taught lessons about entry angles, parachute deployment altitudes, lander robustness, and communication system reliability that inform current mission design even when the specific hardware differs entirely. The Soviet Prop M rover that never deployed from Mars 3 represented a concept that eventually bore fruit in later missions by other nations. The small, tethered rover concept proved too limited, but the idea of mobile exploration evolved into the highly successful American rovers Spirit, Opportunity, and Curiosity, which traversed kilometers of Martian terrain conducting science far beyond what stationary landers could achieve. The technological lineage from Prop M to modern rovers involves wholesale redesign and advancement, but the fundamental insight that mobility enables better science remained valid. Soviet engineers who conceived Prop M anticipated correctly that rovers would revolutionize planetary exploration, even though their specific implementation never got the chance to prove itself. The harsh reality of Mars, as revealed by decades of exploration, shows a planet simultaneously familiar and alien. The landscapes photographed by various missions display features recognizable from Earth: mountains, valleys, craters, dunes, but composed of materials and shaped by processes that differ in detail. The thin atmosphere creates weather including clouds and dust storms, but lacks the complexity of Earth's climate with its oceans and biological influences. The geology preserves ancient history in ways that Earth's active plate tectonics and erosion have erased, making Mars a museum of planetary evolution that can be read by careful study. The potential for subsurface habitability keeps alive hopes that life might exist on Mars today, hibernating in protected environments, waiting to be discovered by future missions that can drill into the subsurface or access caves and lava tubes. The subsurface water reservoirs detected by later missions represent one of the most significant discoveries about Mars, with implications for both science and future exploration. Water ice exists at high latitudes near the surface, becomes more abundant with depth, and may include liquid water in deep aquifers where pressure and temperature conditions permit. The presence of this water opens possibilities for extracting it to support human missions, processing it into oxygen for breathing and hydrogen for fuel, using it to grow food in greenhouses. The water also represents the most promising environment for finding existing life, protected from radiation and temperature extremes, potentially harboring organisms that metabolize chemicals rather than relying on sunlight. Soviet missions contributed to the discovery of Martian water through their measurements of atmospheric humidity and detection of water ice clouds, adding data points to the growing understanding of Mars's water inventory. The detection of methane in Mars's atmosphere by later missions created excitement and controversy in the scientific community. Methane on Earth is produced primarily by biological processes or by geological activity involving water and rock at elevated temperatures. Its presence on Mars in variable concentrations that change seasonally suggests an active source, but whether that source is biological, geological, or something else remains uncertain. Soviet missions did not have the capability to detect methane, but the instruments they carried for measuring atmospheric composition represented early attempts at the kind of atmospheric chemistry that later missions pursued with far more sophisticated equipment. The question of Martian methane illustrates how exploration raises new questions, even as it answers old ones. How each mission reveals complexities that demand further investigation. The discovery of organic molecules on Mars by recent missions challenged earlier assumptions that the Martian surface was entirely inimical to organic chemistry. The molecules detected are simple compared to the complex biochemistry of living organisms, and their presence doesn't prove that life exists or ever existed on Mars. but it demonstrates that the building blocks of life are present. Soviet missions searched for organics with relatively simple instruments that might not have detected the low concentrations found by later missions. But the negative results from Soviet experiments contributed to the initial view that Mars's surface was organically barren, a view that has since been revised. The evolution of understanding about Martian organic chemistry demonstrates how scientific consensus changes as new data becomes available, how early findings interpreted as definitive sometimes prove to be artifacts of measurement limitations. The seismic activity detected on Mars by later missions revealed that Mars remains geologically active despite lacking plate tectonics. Marsquakes occur regularly, though generally with lower magnitude than earthquakes, indicating that Mars's interior still contains heat and that stresses continue to accumulate and release in the Martian crust. This internal activity has implications for understanding Mars's thermal evolution, for interpreting surface features that might be young rather than ancient, and for assessing volcanic hazards that might affect future human missions. Soviet missions did not carry seismometers that successfully operated on Mars, though such instruments were planned, so the discovery of Martian seismicity awaited later missions. The presence of seismic activity makes Mars more dynamic than a dead world, suggesting processes that continue to shape the planet. The oxygen production experiments conducted by recent missions demonstrated that resources needed for human life support can be extracted from the Martian environment. The MOXIE experiment aboard the Perseverance rover successfully converted carbon dioxide from Mars's atmosphere into oxygen through electrochemical processes, proving that in-situ resource utilization is feasible. This capability is essential for sustainable human presence on Mars, as transporting oxygen from Earth would be prohibitively expensive given the mass requirements for breathing and rocket propellant. Soviet planners anticipated the need for resource utilization, including concepts for extracting water from soil and producing propellants on Mars, but the technology to implement these ideas matured only decades after Soviet Mars missions flew. The continuity of concepts across generations of missions demonstrates how exploration builds on foundations laid by earlier work. The vision of human presence on Mars that motivated both Soviet and American programs during the Cold War remains unfulfilled more than 50 years after the first Mars missions. The technical challenges of getting humans to Mars safely, sustaining them on the surface, and returning them to Earth continue to exceed current capabilities, though progress continues. The political will and economic resources required for crewed Mars missions remain uncertain, fluctuating with changing priorities and leadership in spacefaring nations. The lessons learned from robotic exploration inform planning for eventual human missions, with decisions about landing sites, resource availability, and surface hazards based on data accumulated over decades. The Soviet contribution to this knowledge base, though smaller than later missions achieved, forms part of the foundation upon which current understanding rests. The technological artifacts that survived from the Soviet Mars program exist in various states: flight-ready spacecraft that never launched due to mission cancellations or program terminations rest in museums, providing physical examples of Soviet engineering that can be studied directly. Engineering models and test articles survive in storage, sometimes in poor condition due to years of neglect and the economic chaos following the Soviet collapse. Documents and photographs preserved in archives offer glimpses into design processes and mission operations. The people who built and operated these missions, those who survive, carry irreplaceable knowledge about how decisions were made, how problems were solved, how the program functioned at the human level beyond what documents record. The totality of this preserved material represents an incomplete but valuable historical record of an ambitious program that pushed the boundaries of what was possible. The secrecy that characterized the Soviet Mars program created a dual history: the public narrative of achievements announced through official channels, and the hidden reality of failures and struggles that only gradually emerged. This duality makes the historical reconstruction challenging, as sources must be evaluated critically, recognizing that official Soviet announcements represented propaganda as much as information, that Western intelligence reports reflected incomplete data and analytical assumptions, that personal recollections are colored by time and perspective. The truth emerges from synthesis of multiple sources, cross-referencing claims, identifying patterns, acknowledging uncertainty where evidence is lacking or contradictory. The history of Soviet Mars exploration thus remains partially indeterminate, with some details likely lost forever. But the major contours are reasonably well established through decades of research by space historians. The question of how Soviet Mars exploration might have proceeded differently under alternative circumstances invites counterfactual speculation. If resources had been less constrained, if technical problems had been solved earlier, if political pressure had been less intense, might the program have achieved greater success? The challenges of Mars exploration proved difficult for all nations that attempted it, with American missions also experiencing significant failures alongside their successes. Perhaps the Soviet approach of attempting ambitious goals with limited resources was fundamentally flawed, trying to achieve too much too quickly with insufficient testing and reliability. Perhaps different leadership would have made different choices, emphasizing incremental progress over spectacular attempts. Perhaps the classification and secrecy themselves contributed to problems by limiting information sharing and creating political pressures that distorted technical decision-making. The comparative history of Soviet and American Mars exploration reveals different institutional approaches to managing technical programs. American missions benefited from more extensive testing, more conservative mission designs that accepted less ambitious objectives in exchange for higher reliability, and more transparent reporting that allowed learning from failures without political embarrassment. Soviet missions attempted more ambitious objectives with less mature technology, operated under intense secrecy that concealed failures but also prevented broader learning, and suffered from political pressures that created unrealistic schedules and expectations. Neither approach proved uniformly superior, with both achieving successes and experiencing failures. But the American approach delivered more consistent results over time, while the Soviet approach achieved occasional spectacular successes alongside many hidden failures. The role of individuals in determining program outcomes deserves recognition. Key figures like Sergei Korolev shaped the early Soviet space program through force of personality and technical vision, driving programs forward through political obstacles and resource constraints. The engineers and scientists who designed experiments, calculated trajectories, and operated missions contributed expertise without which nothing would have succeeded. The political leaders who allocated resources and set priorities determined what was possible at a programmatic level. The technicians who assembled spacecraft and prepared rockets for launch executed the detailed work that determined whether designs functioned as intended. The distributed nature of responsibility in large technical programs makes it difficult to assign credit or blame to individuals, but the human dimension remains essential to understanding how and why things happened as they did. The Soviet Mars program existed in tension between its practical objectives of advancing scientific understanding and its symbolic role in Cold War ideology. The science motivated many participants who genuinely wanted to understand Mars, to contribute to human knowledge, to explore unknown frontiers. The political imperatives motivated others who saw space achievements as tools of statecraft, as demonstrations of national capability, as propaganda opportunities. These different motivations coexisted uneasily, with political demands sometimes overriding technical judgment, with scientific objectives sometimes sacrificed for schedule or political considerations, with conflicts between what engineers knew was possible and what political leaders demanded. The program's outcomes reflected this tension, achieving less than hoped scientifically, but serving political purposes through its mere existence, as demonstration of Soviet ambition and technological reach. The long-term perspective on Soviet Mars exploration reveals a program that contributed to human capability despite its failures. The development of deep space technologies, the advancement of planetary science, the training of engineers and scientists who carried their expertise into later projects. These outcomes have value beyond the specific mission results. The program demonstrated that Mars exploration was possible, that spacecraft could survive the journey even if landing remained difficult, that international cooperation could emerge even during the Cold War through shared scientific interests. The failures taught lessons that benefited subsequent explorers, preventing repetition of mistakes, clarifying what approaches did not work. The successes, though limited, provided hope that deeper understanding of Mars would eventually emerge through sustained effort. The silence that surrounded Soviet Mars failures for decades represented both a practical security measure and a cultural phenomenon. Soviet society operated on principles that valued collective success and concealed failure, that presented an image of continuous progress toward communist ideals, that treated setbacks as embarrassments to be hidden rather than problems to be openly addressed. This cultural approach to failure extended beyond the space program to many aspects of Soviet life, creating a society where official narratives diverged systematically from lived experience, where citizens learned to read between lines and interpret silences. The space program's secretiveness fit naturally into this broader pattern, representing not just classification for security purposes, but a cultural preference for maintaining appearances over acknowledging problems. The dissolution of Soviet secrecy following the USSR's collapse revealed the extent of what had been hidden. The Western space community learned of missions that had been suspected but never confirmed, discovered details of failures that had been completely concealed, gained access to hardware and documentation that had been inaccessible for decades. This revelation transformed historical understanding of Soviet space achievements, providing context that made the actual accomplishments both more impressive and less singular than propaganda had suggested. The Soviet space program emerged as technically capable but troubled, achieving remarkable feats while experiencing catastrophic failures, driven by talented individuals working under enormous pressures within a system that imposed severe constraints. The engineering documentation from Soviet Mars missions, where it survives and has been made accessible, reveals meticulous attention to detail alongside evidence of resource limitations and schedule pressures. Design drawings show careful calculation of structural loads, thermal conditions, and system interfaces. Test reports document the procedures used to verify that hardware met requirements, noting problems discovered and solutions implemented. Failure investigation reports, where available, demonstrate systematic approaches to understanding what went wrong, analyzing telemetry, examining recovered hardware, testing hypotheses about failure modes. The professionalism evident in this documentation contrasts with the political context of concealment and propaganda, suggesting that engineers maintained technical standards, even when program management and political oversight created difficult conditions. The recovery and analysis of Soviet Mars hardware that reached Earth provides physical evidence supplementing documentary records. When spacecraft failed to escape Earth orbit, some re-entered over Soviet territory where fragments could be recovered and examined. The analysis of failed components revealed manufacturing defects, design weaknesses, and evidence of what occurred during flight. This forensic work informed subsequent designs, identifying problems that needed correction and verifying or refuting hypotheses about failure causes. The physical evidence carried authority that reports and telemetry alone could not provide, confirming actual conditions rather than relying on measurements or calculations that might contain errors. The human cost of the Soviet Mars program included not just the careers devoted to it, but also the personal sacrifices required by the closed society in which it operated. Families of engineers working on classified programs lived with restrictions on travel, communication, and association that limited their freedom and opportunities. The stress of demanding work, combined with political pressure, created health problems for many participants. The disappointment of repeated failures took psychological toll, creating cynicism and burnout that affected some, while others maintained commitment through determination or belief in the ultimate importance of the work. The rewards for those who participated included professional achievement, relatively good living standards by Soviet norms, and the satisfaction of contributing to endeavors that pushed human capability, but these came at costs that participants paid in various ways throughout their lives. The question of whether the Soviet Mars program justified its costs admits no simple answer. By narrow economic calculation, the limited science return and minimal practical benefit suggest poor return on investment. By broader measures that include technology development, training of personnel, and demonstration of national capability, the value appears greater but remains difficult to quantify. By the standards of historical significance and contribution to human knowledge, the program clearly mattered, advancing planetary exploration despite failures, contributing data that informed understanding of Mars, demonstrating both the possibilities and difficulties of interplanetary spaceflight. The judgment depends on which values one prioritizes, how one weights different kinds of outcomes, and whether one considers counterfactuals about what else might have been done with the resources invested. The legacy of Soviet Mars exploration lives on in multiple forms. The institutional structures and facilities created for the program continue operating as part of modern Russian space efforts. The technologies developed found applications in subsequent missions to various destinations. The knowledge gained about Mars contributed to the global scientific understanding that continues to grow. The lessons learned informed the design of later missions by many nations. The inspiration provided to individuals who participated or observed the program influenced career choices and research directions. The historical example serves as case study for understanding how complex technical programs function under political and resource constraints, offering lessons for contemporary efforts in space exploration and other ambitious technological endeavors. The comparison between what Soviet planners envisioned for Mars exploration and what they actually achieved reveals the persistent gap between aspiration and reality in ambitious technical programs. Plans called for surface rovers traveling kilometers, for sample return missions bringing Martian soil to Earth, for networks of landers covering multiple locations, for extended observation campaigns from orbit. Reality delivered brief surface operations, intermittent orbital coverage, and much less data than hoped. This gap reflected the immense challenges of working at the edge of technical capability, where optimism about what should be possible confronts the stubborn difficulties of making complex systems work reliably in extreme environments. The persistence of this gap across decades and across different national programs demonstrates that Mars exploration simply is difficult, regardless of approach or resources. The technological maturation that eventually enabled more successful Mars missions occurred gradually through accumulation of experience and capability. Electronics improved in reliability and capability, allowing more sophisticated instruments and spacecraft systems. Computers became more powerful while requiring less power and mass, enabling better autonomous operations. Communication systems improved in sensitivity and data rate, allowing more information transfer. Understanding of Martian environment deepened, informing better designs for entry systems, thermal control, and surface operations. Manufacturing improved in precision and quality control, reducing failures due to defects. Testing capabilities expanded, allowing better validation of designs before flight. This gradual advancement meant that missions flying decades after Soviet attempts could accomplish what earlier missions could not, building on accumulated knowledge and technology. The scientific questions about Mars that remain unanswered continue to justify exploration. The presence or absence of life, past or present, remains uncertain despite decades of investigation. The detailed history of Martian climate and how it changed from apparently habitable conditions to current harsh environment requires further study. The interior structure and composition need better characterization through seismic and other geophysical measurements. The distribution and accessibility of water and other resources important for future human missions require more extensive surveying. The hazards posed by dust storms, radiation, and other environmental factors need better understanding to enable safe human operations. Each mission that returns data answers some questions while raising new ones, advancing understanding while revealing deeper complexity. The ethical dimensions of Mars exploration have evolved as the possibility of finding life became more realistic and as plans for human presence advanced. The question of planetary protection, preventing contamination of Mars with Earth organisms, or contamination of Earth with potential Martian organisms, requires careful protocols for spacecraft sterilization and sample handling. The question of whether humans have the right to alter Mars through terraforming or exploitation raises philosophical issues about our responsibilities toward other worlds. The question of how to share access to Mars among nations, and whether space resources can be claimed by those who reach them first, involves international law and policy. These ethical considerations were less prominent during the Soviet program when finding life seemed unlikely and human missions distant, but they become increasingly important as exploration advances. The Soviet Mars program operated during an era when the space frontier seemed to be opening rapidly, when progress appeared linear and inevitable, when expectations for space development exceeded what proved technically and economically feasible. the disappointment of unfulfilled visions, the absence of lunar bases, the lack of crewed Mars missions, the failure of space industrialization to materialize, reflects the gap between mid-20th century optimism about space and the reality of sustained space activity requiring enormous resources with uncertain returns. The Soviet Mars missions participated in this optimism, attempting ambitious objectives that assumed rapid advancement would continue, learning through failures that space exploration was harder than anticipated. The slower, more incremental progress that actually occurred may be less inspiring than visions of rapid expansion, but it has proven more sustainable. The alternative history where Soviet Mars missions succeeded more substantially would have altered the trajectory of space exploration in ways difficult to predict. Greater Soviet success might have intensified competition, driving larger investments by both superpowers in planetary exploration. Or it might have reduced American motivation, eliminating the imperative to outperform Soviet achievements. Soviet successes might have generated domestic political support for even more ambitious missions, or might have satisfied political leaders who would then redirect resources elsewhere. The counterfactual branches proliferate rapidly, demonstrating how contingent historical development is on specific events and decisions. The actual history we have, with Soviet struggles and modest American successes in Mars exploration, shaped a trajectory where Mars remained scientifically interesting but politically secondary to other space priorities. The cultural impact of Mars exploration extended beyond the space community to influence broader society. Mars appeared in science fiction with renewed prominence, informed by actual data from missions that revealed the planet's real characteristics. Artists created works inspired by images from Mars, interpreting the alien landscapes through various media. Educators used Mars missions to teach science and inspire students toward technical careers. The general public followed major missions with varying degrees of attention, with some becoming deeply engaged while others remained indifferent. The Soviet public learned little about Mars missions due to sparse official coverage and the concealment of failures, experiencing the space program more through propaganda about achievements than through engagement with the actual process of exploration with its uncertainties and setbacks. The transition from Soviet to Russian space activity involved not just political change, but fundamental transformation of how the program operated. The loss of centralized planning and guaranteed funding forced the Russian program to seek commercial customers, to participate in international collaborations for financial reasons, to prioritize missions that could attract support over those with primarily scientific objectives. The brain drain as talented personnel left for better opportunities abroad or in other industries depleted expertise. Facilities deteriorated due to inadequate maintenance funding. The continuity of institutional knowledge was broken as retirements and departures removed experienced personnel faster than new staff could be trained. These disruptions created a gap between the Soviet-era program and subsequent Russian efforts, with consequences for capability that persist decades later. The international collaboration in Mars exploration that developed after the Cold War contrasts sharply with the competitive secrecy of the Soviet era. Modern missions often involve instruments contributed by scientists from multiple countries, data shared openly through international archives, and coordination to avoid duplication of effort. This collaborative approach increases scientific return per mission and builds relationships among space agencies and research communities. The Russian space program participates in this collaboration despite diminished capabilities, contributing expertise in areas where Russian technology remains strong, while benefiting from partnerships that enable participation in missions Russian resources alone could not support. The evolution from competition to collaboration represents one of the positive transformations in space activity following the Cold War's end. The Mars program's place in Soviet space history reflects both its limited success compared to Luna and Venera programs and its role in pushing technological boundaries. Mars missions attempted more ambitious objectives than lunar missions in some respects, requiring longer transit times, more sophisticated entry and landing systems, and acceptance of longer communication delays. The modest returns from Soviet Mars missions compared to the resources invested made the program vulnerable to cancellation as priorities shifted. The persistence of the program through repeated failures demonstrates commitment, but also perhaps institutional inertia and political investment in continuing efforts already begun. The ultimate winding down of Soviet Mars efforts reflected rational allocation of limited resources toward programs with better success records, even as the scientific allure of Mars remained strong. The lost missions of the Soviet Mars program, the spacecraft that exploded, burned up, fell silent, or crashed, exist now only in fragments. Scattered documentation, memories of aging participants, wreckage buried in steppe or ocean floor, and the handful of machines that reached Mars but never functioned as intended. These lost missions represent enormous effort and investment that produced minimal direct return, but maximum education about the challenges of planetary exploration. Each failure taught lessons, shaped subsequent designs, contributed to the gradual accumulation of knowledge required for success. The waste implied by failure is real, but the learning is also real, and subsequent missions benefited even if the immediate crews who experienced the failures found little consolation in that long-term perspective. The question of what physical traces Soviet Mars missions left on Mars includes the Mars 2 impact site, where fragments of the crashed lander lie buried or scattered on the surface, and the Mars 3 landing site, where the lander and its undeployed Prop-M rover rest beneath decades of accumulated dust. Future Mars explorers, whether robotic or human, might someday locate these sites and examine the remains of humanity's early attempts to reach Mars. The landers would appear antiquated compared to later technology, their electronics crude, their mechanical systems simple, but they would testify to the courage and ambition of those who built and launched them into the unknown. The archaeology of early space exploration includes these artifacts on other worlds, time capsules preserving technology, and intentions in forms that might survive far longer than documentation on Earth. The Soviet Mars program ended not with definitive cancellation, but with gradual fading as resources and political support evaporated. The last missions flew in the 1970s, with later plans remaining unrealized as other priorities dominated. The institutional knowledge and capabilities atrophied without missions to maintain them, even as American and later European missions continued advancing Mars exploration. The Russian Mars 96 mission represented attempted revival, but ended in catastrophic failure that seemed to confirm Mars remained beyond Russian reach. Later Russian Mars efforts have focused on collaboration with other nations rather than independent missions, accepting secondary roles in exchange for participation. The trajectory from Soviet ambition to Russian retrenchment reflects broader patterns in space exploration as initial Cold War drivers dissipated and economic realities imposed constraints. The full accounting of the Soviet Mars program remains incomplete and likely will always be so. Documents destroyed or never archived, hardware scrapped or lost, participants deceased without leaving records, memories faded or never shared, all contribute to gaps in historical knowledge. The reconstruction that historians have accomplished provides a reasonable outline of what occurred, when, and with what results, but many details remain uncertain or unknown. The exact reasons for specific technical failures, the internal debates about program direction, the political considerations that shaped decisions, the personal experiences of those involved, these human dimensions of the program are fragmentary at best. Future discoveries of documentation or hardware might fill some gaps, but the passage of time makes complete reconstruction increasingly unlikely. The Soviet Mars program stands as testament to human ambition confronting hard reality. The drive to explore Mars, to achieve firsts, to demonstrate capability, to advance knowledge, these motivations produced genuine effort and accomplishment despite failures. The program pushed technological boundaries, developed capabilities, trained people, and contributed to human understanding of Mars and of what planetary exploration requires. The failures humbled but did not destroy the program, which persisted through repeated setbacks demonstrating both resilience and perhaps stubbornness. The outcomes fell short of hopes but exceeded what might seem possible given the limitations under which the program operated. The assessment of success or failure depends on perspective, on what one values, on whether one measures achievement against aspirations or against starting conditions. The silence that hangs over failed Soviet Mars missions, the classification that still restricts access to some records, the gaps in public knowledge, These absences shape historical understanding as much as available evidence. The things we do not know create space for speculation, for conflicting interpretations, for ongoing debate about what occurred and why. The gradual opening of archives and emergence of information improves understanding, but slowly, with each revelation prompting questions about what else remains hidden. The historiography of Soviet space programs continues to evolve as new sources emerge, as analysts develop new interpretations, as context from other historical research illuminates aspects previously obscure. The history remains alive, subject to revision, incomplete but progressively more complete as time passes and information accumulates. The engineers and scientists who conceived, designed, built, and operated Soviet Mars missions worked within constraints that shaped what they could accomplish. Limited budgets compared to the ambitions they held, technology that lagged in some areas, political pressures that distorted technical decision-making, secrecy that prevented learning from others' experiences, these factors created an environment where success was difficult and failure common. Yet within these constraints, dedicated professionals produced remarkable machines that traveled millions of kilometers through space, entered orbit around another planet, and landed on alien surfaces. The accomplishment deserves recognition even when outcomes disappointed. The effort matters even when results fell short. The contribution to human capability persists even when specific missions failed. The Soviet Mars program ultimately revealed as much about human limitations as about Mars itself. The difficulty of predicting and preventing failures in complex systems, the challenges of working across vast distances with communication delays, the problems of building reliable hardware under resource constraints, the tensions between technical judgments and political demands. These human factors shaped outcomes as much as technical factors did. The missions served as experiments in what humans could accomplish through organization, technology, and determination. Experiments that produced mixed results, teaching humility alongside confirming capability. The program demonstrated that reaching Mars was possible but not easy, that landing was achievable but not simple, that sustained operations required solving problems that remained unsolved through the Soviet era. The long silence of Mars 3 after 90 seconds of transmission echoes through subsequent decades as symbol of how close success came and how completely it eluded Soviet efforts. The lander functioned just long enough to prove its systems worked, then died before accomplishing its mission, embodying the pattern of promise and disappointment that characterized the broader program. The Prop-M rover that never rolled, the science instruments that never measured, the camera that never imaged. These unrealized potentials haunt the historical record, representing what might have been had conditions been slightly different, had the dust storm been less severe, had the engineering been slightly more robust, had luck favored the mission. The counterfactual successes that almost occurred tantalizes more than complete failures that never came close. The Soviet Mars program created infrastructure, developed technology, trained personnel, and established procedures that outlived the missions themselves. The tracking stations, though aged, continued serving later space efforts. The expertise in spacecraft design, though diminished by departures and retirements, persisted in institutional memory and influenced subsequent work. The scientific community built around planetary research continued studying Mars using data from other nations' missions, contributing analytical perspectives enriched by Soviet experience. The legacy proved more durable than the specific missions, with effects rippling forward through subsequent decades in ways both visible and subtle. The story of Soviet Mars exploration resists simple telling, fragmented across time and sources, obscured by secrecy and losses, complicated by technical detail and political context. The narrative emerges incompletely from accumulated fragments, mission designations hiding more than revealing, brief telemetry before silence, scattered documentation, aging memories, physical artifacts bearing witness to vanished intent. The full history likely exceeds what can ever be reconstructed, with portions lost permanently to document destruction, death of participants, and fading of memories. What remains allows partial understanding, enough to appreciate ambitions attempted and challenges faced, enough to recognize both achievements and failures, enough to situate Soviet efforts within the broader human enterprise of exploring Mars that continues building on foundations they helped establish despite their struggles.